You all have probably heard of some eco-friendly ways to improve air quality and clean CO2 from the air. But have you guys ever heard of photobioreactors? Let's learn about it. A photobioreactor is a closed system designed to grow microalgae using light, water, and carbon dioxide. Inside the system, microalgae performs photosynthesis, converting carbon dioxide into oxygen and biomass. Because the reactor is enclosed, operators can control variables such as light intensity, temperature, and nutrient levels. This allows the system to replicate the natural carbon cycle in a measurable and consistent way. Photobioreactors are used for research on carbon capture, algae growth, and material production. According to Dr. Ivan, a scientist who founded the Serbian company Liquid 3, said that utilizing microalgae within photobioreactors actually improves air quality 10 times to 50 times to even 400 times more than trees. To understand how these systems function on a technical level, let's take a closer look at their engineering design.
A photobioreactor works by introducing CO2-rich air into water containing suspended microalgae. With sufficient light, whether from sunlight or LED sources, the algae uses CO2 as carbon source for growth. Several engineering components help maintain stable operation. Sensors track pH, temperature, gas levels, nutrients. Pumps circulate the water to improve gas exchange. Because it is a closed-loop design, the reactor minimizes outside contamination and produces more reliable data. This setup allows for continuous measurement of CO2 absorption, oxygen release, and algal productivity. Now that we looked at how the technology works, the next question is where it can be most effectively tested. That's where government buildings come in.
Government buildings tend to have predictable patterns of occupancy, which result in steady indoor CO2 levels from human respiration. This consistency makes them useful environments for observing how photobioreactors perform under everyday conditions. Public buildings also maintain stable indoor temperatures and lighting schedules, which helps support accurate measurement of system behavior. Installing photobioreactors in these locations allows operators to collect real-time environmental data, including CO2 changes and algae growth rates. These sites are often used for pilot testing before considering broader adoption in other settings such as schools or offices. Understanding their location helps set the stage for what these systems can actually achieve. Let's look at the environmental and practical observations.
Photobioreactors can influence indoor air composition by reducing measurable CO2 concentrations, depending on their design and the scale of the system. As microalgae absorb carbon dioxide, they release oxygen, which can alter indoor air balance. The reactors also generate data on carbon uptake rates, energy use, and growth efficiency, making them very valuable tools for evaluating biological carbon capture in controlled environments. Additionally, the algae produce biomass that can be examined for potential applications or stored for research purposes. These observations help determine how effective photobioreactors are when operating in real building conditions. Together, these systems provide measurable information that can guide future decisions about sustainability and indoor air management.
We, Air Group number 8, hope you found this video interesting and inspiring. And who knows, maybe photobioreactors are the future.